we talk about plutonium?
Let's talk about plutonium.
Let me do a little introduction.
You tell me.
I don't know what to say. You do it. You do it.
All right. All right. Intro papers today. What have we got? We've got. It's a bit of a double whammy, but that's because the first one that I pulled out was like not even a half page. It was tiny wee.
It was really little.
I needed more content. So we've got two papers today. So we've got radioactive element 94 from deuterons on uranium. Pardon me. This was by published date. This is the 7th of March 1941. Published date by submitted date. Sorry. This is the University of Berkeley team. Seaborg, Wall, and Kennedy. Oh, I thought there was a Macmillan in here.
There is a Macmillan in here. I think he's in the second paper.
He's not in the second paper. I don't see it in the second paper.
There's definitely a
He's
Macmillan.
in the team. I've seen a Macmillan around. Anyway, and then paper 2, we've got properties of 94. So 239.
Macmillan's in the second paper.
I can't see him. I don't see him in that. Are you sure?
Yeah, the second page.
No, he's not.
By the method of Macmillan and Abelson.
Oh, okay. Well, yeah, he's referenced. I think he's in the team, but he wasn't necessarily on the.
I was going to ask you if that was your great granddad or something. I know it. I know it isn't because I've met your grandparents, but
it's not my great grandparent. So 94 or element 94 at the time is referring to the atomic number of this element. Yeah, and so these are elements that are heavier than uranium. So uranium at the time was known and radioactivity was a thing, but this is can we make heavier and cooler elements beyond uranium? So they were
uranium,
I got
of course,
some history.
Uranium, of course, atomic number 92. And I found it really interesting looking at this paper for the first time because it is just called element 94.
They don't even say plutonium.
I wonder when its name came in.
I think it was like shortly thereafter.
Yeah, must have
from
been.
the wiki page. But...
Yeah, very interesting. Yeah. Very interesting. Another path down historical lane.
History time.
Yeah. Who knew this was a history podcast, eh?
Can you tell us why we're talking about plutonium, Callum?
So I found it was like a YouTube video or something about the demon core, which sounds really cool. And I've got the wiki page open next to me, and that'll be on the video for those that want to see. So it says on the wiki page.
But if you're an audio listener, sorry.
If you're an audio listener, I'm about to read it to you, so it's not the end of the world.
Oh, it's okay.
It says the demon core was a sphere of plutonium that was involved in 2 fatal radiation accidents when scientists tested it as a fissile core of an early atomic bomb. It was manufactured by the Manhattan Project, the U.S. nuclear weapon development effort during World War II. It was a subcritical mass that weighed 6.2 kilos and was 8.9 centimeters in diameter. So very little. And I'm pretty sure I saw like I mean, obviously it wasn't like a video of it, right? It was, I imagine it was some sort of a reenactment, but I just thought it looked really cool. And then I was like, can we just talk about radiation? Because radiation is one of those things that it scares out of me. So like as a teacher, occasionally we have to get the radioactive isotopes out. And I'm like, generally when we do practicals in school, nothing can really hurt you, yada yada yada. But like when I'm holding alpha or beta emitters, it demands a level of respect that other things don't necessarily demand as quickly, and I find that terrifying and awesome. And like I truly believe that like the scariest sound in the universe is the click of a Geiger counter. Like there is no sound that makes me more uneasy than the click of a Geiger counter. So yeah, I just figured let's talk about radiation.
Nice. That's actually interesting. So my thesis was related to radiation. I've actually spent a lot of time thinking about radiation, but I don't think beyond school I've been anywhere near or done anything with actual radioactive elements. So you're probably more familiar with that part than me.
The handling,
whenever I think
perhaps.
like when I think about so we in some previous work we were doing radiation testing of components, and it just gave me the heebie-jeebies. Like, you mean this thing here has been subjected to radiation, and I can just touch it now? Can I touch it? Is it radioactive? Oh, I just don't want to. I don't want to get near it. I
Yeah,
don't like it. Yep,
it does
not a fan.
it makes me super uneasy. But I really love talking about it, and it's one of those topics in school that like the kids buy into. You know, they really want
Mhm.
to learn about it. You know, everyone has heard of like Chernobyl and stuff like that, and everyone just wants to talk and explore and learn and engage. So it's from like a teaching and learning point of view, it's really nice because you don't have to battle so much with behavior, I don't find. But
Interesting.
certainly from a me point of view, it is as I say, it makes me feel a little bit uneasy to hold something that, you know, could cause harm in that way.
Mhm.
It's
Mhm.
scary stuff.
Um, can we have a little TLDR of what is radioactivity, fission, fusion, alpha, beta, gamma?
Yes, I love that you asked me to do that. It's good actually
I feel
because
like you've got that down pat.
well, it's good as well because you can vet my knowledge and make sure I'm not chatting rubbish. Um, so my understanding of radiation is it's caused by unstable large isotopes of atoms. Um, when they are unstable, they will emit some of their energy away in one form or another, either as alpha, beta, or gamma decay. Alpha decay, we talk about it as being the least penetrative but the most ionizing in terms of its properties. So an alpha particle is just a nucleus of helium without its electrons. So it's got a mass of 4 and quite a large positive charge. And if you that gets inside your body, it would wreak havoc upon your bodily systems, tearing electrons off of the atoms in your body and rendering you
Devastating.
pretty acutely sick and shortly dead. Um, Beta is a high energy electron, and this is a really interesting point. So when beta decay happens, and make sure I get this around the correct way, is it a neutron turns into a proton and then emits the beta particle, which is a point of confusion for kids for sure because the atomic number actually changes. Is it the other way around? You're
I don't know.
shaking your
I don't
head.
know. No, I got no idea on that one.
I'm just gonna double check
Let's assume you are correct.
before I put out fake news. Beta decay. Before I put out fake news. So beta plus decay is a proton being converted to a neutron, and beta minus decay is the opposite, a neutron. So I was correct.
Alright, alright. Nice,
Yeah. So
nice, nice, nice.
it is it's a bit weird. I've got doggy. Doggy wants to come for a cuddle. Come on, doggy. Doggy's on the video now. And the last one is gamma. Gamma is not a particle. Gamma is an electromagnetic wave. So it's just a big chunk of energy, basically, is how I understand it. Um, so beta is in the middle in terms of ionizing and penetrative power, whereas gamma is much more penetrating and much less ionizing than an alpha particle. You also mentioned fission and fusion. So
Yep.
fission is the splitting of an atom into two
Hmm.
constituent atoms, and in that process of splitting, it will emit radiation, alpha, beta, or gamma, depending on what it is. Um, and fusion is the opposite. Fusion is what happens in our sun, in our local star. It's the joining of atoms together, which again releases an enormous amount of energy. And it looks like Wilma's released an enormous amount of energy today because she's very sleepy. She's just gonna chill here for a bit now.
Just gonna just rest. Nice
Good
to
for
see you,
her.
Wilma.
Yeah, nice to see you, Wilma. For
Nice.
those audio listeners, get on YouTube. She's super cute.
Bit blurry, but
Yeah,
cute.
I think that's because I've got a fuzz on my camera, and it's not, it's not a very expensive MacBook camera. What I've got here, it's just a little Logitech. It does the job though.
um, what was I thinking? Uh, you said gamma's not a particle and it's a wave. wave particle duality.
Yeah, I thought you might say that. So now we're
That's
we're
good
going
stuff.
down the double slit experiment.
This is
Uh,
far too deep of a tangent.
I
But
mean,
yeah, in principle,
sure,
I like those definitions. They were good. Um, are you? How much do you recall of like the from like the fission side, like from the fusion side of smushing atoms together and getting less and less energy, or like, are you aware of like the inflection point around iron?
not particularly.
Oh,
Enlighten me.
that's a really fun tangent. So if you take the two smallest elements that we have in the universe, which are hydrogen, and you shove them together, I'm if there's anyone listening that actually knows fusion, then this is probably a bit of a mess because there's the whole lithium and the deuterium and the nitrodium and I don't know. You smush the hydrogens together and you
Yeah.
make a helium. You make loads of energy, lots and lots, and it's the most energy that any fusion event can make. If I
Hmm.
was to take a hydrogen and a lithium, and then so lithium's a little bit heavier than a hydrogen, and you smush them together, it'll make lots of energy but a little bit less than
Yep.
my hydrogen reaction. So the idea here of if you start smushing things together, the
Heavier.
heavier they are, the less net energy is produced. And you can watch this
So is
underneath
this
your little
this
clock.
makes me think of like I remember seeing like an old Brian Cox thing where he talks about elements that are made in stars
Mm,
and he talks
mm.
about iron as being the heaviest. Is that where this
That's
is
it.
going? Right,
Yeah,
right,
that's it. So if you track that like net energy gain
right. Come on,
with
good girl.
like smushing
Mwah.
of elements, at the point when you make iron, so I can't remember what you need to shove together for that. I don't know. Defer to periodic table. What's atomic number of iron over two? It's about what 50 something. So something in the 20s. I don't know. Maybe two calciums or something. But you
Silicon
shove those
into
two
iron
together.
apparently. I've just googled it.
All right. Yeah. Okay, there you go. So if you smush some silicon into iron, then the amount of energy it took to smush them together was more than it produced. So it still produces energy, but your net
But your
is a
net,
loss.
yeah.
You
Okay.
now got a net loss. And so if you look at that sort of like progression from through the elements up to iron in stars, so where there's a lot of nuclear fusion happening and you're smushing things together and making energy, at the point when your star then makes iron, you're now at a net loss, and it's a chain reaction from there to make heavier and heavier elements. But then your energy you're producing and the radiation pressure your star is
Your star becomes unstable, whatever.
pushing out is then less than the gravity crushing it, and it starts to go and do fun star stuff.
We get a
So
big
I
boom.
always like thinking about from that end of like fusion end, you get up to iron, and then
And then you're at a
things will
net
go a bit
loss.
pear shaped. Yeah, that's quite good.
Interesting.
And then, so from the other end, if we look at if I took a single atom, a single fissile element like a uranium or a plutonium, and start splitting that apart, it's the heaviest stuff that you start splitting apart that produces the most energy. Um, and so, like if I took some
An event
radioactive iron, say, and then split that apart, I don't know if you can do that, but you'd get only a little bit of energy or
in
whatever.
comparison.
In comparison to uranium. So that's the reason that you'd have like uranium and plutonium as your fissile elements, just because you're bang for buck. It's up.
Yeah. I mean, it certainly puts out a hell of a lot of energy, nuclear fission.
Mm.
Um,
Mhm. Mhm.
I sometimes wonder why on planet Earth we don't have more, uh, you know, I don't know what the word is, resources, space for nuclear energy, more investment
Mm.
perhaps. And then I
Mhm.
remember things like Chernobyl, and I'm like, oh, okay, people are very scared, I suppose. And like, I even think about like me in the classroom with my Geiger counter and my little alpha, and I'm like, yeah, I'm scared enough then.
Yep.
Imagine if they were building one down the road, I probably wouldn't be very happy. So then it kind of makes sense.
Yeah.
But yeah, it would be nice. It would be
They
nice.
got bad PR.
Very bad PR. Very bad
Mm.
PR. But
How
yeah.
were a review of what you do with your nuclear elements
Um,
after they're
what
done?
with
And they've
waste?
they've yeah.
So I saw the movie Godzilla 2014, and
I
in
haven't.
that,
Was it good?
I rate monster movies as a whole, to be fair. But in that they have them like all buried underground in like giant
Mm.
like lead lined caves, basically.
Nice, nice.
I
Who
don't
else was
know.
there? Was
I
there
have
Godzilla?
no idea.
Was there Mothra in there?
Mothra is in one of them. I don't know if
Angui
Mothra's in the first one.
Anguira?
Don't know. Do you remember that game we used to have on GameCube? Was it GameCube? The
The Godzilla
Godzilla
game.
monster fighting one.
Yeah, it's
Mate,
amazing.
do you still have that?
Yeah, it's still just as
Bring
good.
it to mine one day, please. I really want to play that. Ah,
Yeah, all right. We'll whip out the GameCube.
twitch.tv forward
Really
slash
fun.
osmosis Godzilla fighting game.
Mecha Godzilla. So good.
So
Um,
good.
Yeah, so your radioactive waste. I did some research on this back in the
Mhm.
day, but you got different like classifications, and really radioactive stuff gets like encased and then encased, and yeah, got warehouses of the stuff.
I always wonder, like, why don't you just shoot it into space? And then I feel like that's just littering. That's just like,
Yes,
like
that's littering.
we don't want to, like, when you like, I'm not one for littering, but occasionally like you'll be driving along and you just see someone throw a can out the window, and it makes me so angry when I see that, and I'm like,
Mhm.
we can't just throw our rubbish into space, because
Exactly.
one day we might have to leave our planet because we destroy it because of global warming, and then we could, like, I don't know. I'm not one for littering, I guess.
No, let's yeah, not throw up into space.
It's a shame you can't just like chemically break it down further and make it stable, but I suppose that's like,
Well, you can.
well,
No.
if you can, I don't know.
Yeah, no, you probably can't. Or maybe there's just too much of it. It's too much effort.
Well, that's
Just
just
wait for it to
BS.
decay.
What, thousands of years?
Yeah. Yeah, I
I
don't
mean,
know
that
why.
does sound like human beings, to be fair. Ah, it's too big of a job. Just wait a couple thousand years, it will soon be gone.
Yeah.
No,
Man,
because now
nuclear waste.
we're gonna go down a tangent now, and I'm just gonna get enraged at humans. That's what's gonna happen. We need to steer clear of getting enraged of humans today.
Should we step back to the paper? What
Let's
have we
talk
got here
about
then?
the paper. Let's talk. Are we gonna talk about the first one, the half
Yeah,
a
let's have a look
page
at that.
long one?
Let's have a look at that one. So this is radioactive element 94 from deuterions on uranium.
I'm
I
gonna
think an
pause you
interesting.
actually.
What?
Deuterons is heavy water, right? Deuterium.
Deuterium is.
It's heavy hydrogen based water. So hydrogen with a
All
neutron.
right. Are you telling me or are you asking me?
I'm asking you. I'm asking you to
Oh.
clarify my understanding of what that is.
Oh Christ! I don't actually know. I thought it was neutrons. Are they not just the slow neutrons?
See, I thought it was. I'm gonna just
All
Google
right.
it. We just double googling.
Come on. Deuterons. Yeah, I kind of just stepped over it and didn't really think about what on earth it was, but
Deuteron, nucleus of deuterium. Yeah, I was right. So
okay.
it's one proton and one neutron. So hydrogen has
Heavy
one.
hydrogen then.
Yes,
Heavy
so it's
hydrogen.
heavy hydrogen,
Yeah,
but
yeah,
with
yeah.
sans the electrons. And I the only reason
Yeah.
I know a little bit about deuterium is because I have vague memories of using it in NMR and stuff when we were at
Okay.
university, all of those years ago.
Mm-hmm.
So yeah, sorry, I interrupted your train of thought.
Well,
Please continue.
so this is from the radiation laboratory in the University of Berkeley. So an interesting tidbit that I found whilst reading these papers. So when you going through the like paper submission approval process, it's a pain. It's arduous. So the typical thing would be I have a paper, I write it, I submit it to a journal. They come back to me with some reviews from my peers and say, "Oh, this is great, we'll have it," or make it a little bit better, and then let's assume you get a bit better and you resubmit it, then they'll say, "Oh, okay, great, we're going to publish it on this date." So there is a non-zero period of time between I did the work and I wrote the paper to this paper that is now a thing. But you don't often quite see it this long. So it was submitted to the paper on the 7th of March 1941. But this was the footnote is great. The letter was received for publication on the date indicated, but was voluntarily withheld from publication until the end of the war. So
Ah, the old end of the war, eh?
Yeah, wartime secrecy was a thing here. So this is the US researchers had done this work. They're like, we've got this whole plutonium thing, and well, history books will tell you what they did with it, but
Hmm.
they didn't publish it openly until I think it was like 46 or so. When did they? Yeah, so it's published in 1946 in Physics
It's
Review.
mad, isn't it?
Physical Review. Yeah, I thought that was interesting.
It is that is a yeah, I'm with you. That is interesting because they wouldn't want the enemy to get their hands on it, I suppose.
Hmm.
Interesting.
Yeah. So did you follow what was going on? Because I did, but I didn't.
Yeah, much the same. I did, but I didn't. Lots of words that I recognize and things like that. Um, yeah, it was okay. It was good. I didn't mind this one too much. I thought it was easier to follow than Fong,
Hmm.
but it was also considerably shorter, so I imagine that helped. And it was definitely easier to follow than your translated Slim paper.
Yeah, that was a tricky paper. Yeah. Nice. Yeah. Okay. So let's have a look. What have we got? So
Oh,
method, well, the hypothesis they're running here for both of these papers are pretty much if I take my uranium and I bombard it with some slow neutrons. Well, maybe I thought it was slow neutrons, but maybe it's deuterium. You can synthesize transuranic elements. So that's what they're looking to do here. Make me my heavy elements because we're in a cool age of discovery. Um, so the method that paper one here was employing is alpha bombardment of uranium 235. I'm just saying all things here. We've got uranium, neutron, or rather alpha
hmm.
neutrons and deuterons. Something was bombarding uranium 235.
Yes.
Um, but it was how do you? It's not. I have a lump of metal, which is my uranium. I bombard it, and now it magically transforms to my new element. That's not quite what's going on.
If
But
only.
if only. But I think it creates a gas. Maybe it creates a gas. It creates, I think it creates a gas that you can then precipitate in a solution of some. They were talking about like fluoride or iodates, and this is where I'm thinking like I don't know this stuff. Callum might know this stuff. Um,
No, I didn't really
and you can
attend my
precipitate it
final
out.
year of university. It was not a good time.
But you can if you bombard your lump of uranium, you can emit your plutonium not as
Get down.
plutonium atoms, but as a
Good girl.
plutonium ion, and then that can um, what am I thinking here? React with
Mm.
an iodate or fluoride solution, and then when you have that, you can then try and work at getting it out of that precipitate from those solutions. But that's what I understood them to
I
be doing. Does that sound about right?
I mean that sounds deeper than what my understanding was, I suppose. Uh, I don't know. I'm not that great at reading science papers. I get lost in all the words. I feel it will get better, right? Um, I much prefer like your little summarizing just then. Ah,
All right. Okay.
perfect.
Okay. Good. Yeah. I had to read it a bit. Like,
Yeah.
what are you talking about? But that was the gist of what I got them doing. And then in terms of okay, well we've done this thing now what? They what did they say? So they were talking about some beta active indicators. This was all very much lost on me.
Are we definitely
Um,
looking at the right paper, by the way? The same one? Because
tiny
now,
little short one.
yeah, the little shot. Okay, we are. We are good. Good. Good.
Yeah,
Good.
yeah,
Good.
it's on the like second half. They discuss using a beta active UX1 as an indicator. I don't know what that is as an indicator for thorium. Um, but at least these early results were saying we can bombard uranium with this whatever they bombarded it with. Was this in the cyclotron? Yep. So this is in a cyclotron, um, and we see something. We don't think it's uranium. We think it's something else, and that's kind of it. That was where they left this paper off, which was fine. Yeah.
I mean, to us today, it seems crazy that you know obviously this was a time when it was all so much unknown,
Mhm.
right? It's like completely novel stuff back in the 40s.
Yep. 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 The thing that still baffles me is like, how do you know that you've got a different thing? Like, you're
Mm.
telling me it's plutonium, but how? And like, I guess reading some of this paper gave a bit of an indication as to how they know that. So they know properties or how a uranium might behave, and then they can
hmm
say, well, it's not that, it's this other thing.
hmm
So, yeah, that was interesting. Do you know what a cyclotron is, Callum?
I'm assuming it's something that spins things really quickly, but I don't
I don't
know.
think it is. Oh, okay.
I don't know.
Um,
I'm just
su-
guessing off of the cycle in the name.
the Large Hadron Collider. Do you know what that is?
hmm
Yeah, I think cyclotron's one of those, just tiny,
Hmm.
on a lab scale, rather than a national scale, international scale.
I
Um,
mean, I was kind of right then. Something that spins things around.
it does spin things around. It doesn't spin around our uranium, but yeah. So a cyclotron is a, I don't really know this, but something that can accelerate particles really fast, so then you can smush them into
Would you like me to give
something.
you the definition from the International Atomic Energy Agency, whatever that is, top hit of Google?
IAEA? Yes,
Yeah.
please.
A cyclotron is a type of particle accelerator which repeatedly propels a beam of
Mm,
charged particles, protons, in a circular path.
there you
So
go.
it is a big
That's
thing
it.
that spins things around.
Yeah, I guess it is. They're really cool.
It's the
Particle
Small Hadron
colliders.
Collider, shall we say. That's what a
Yes.
cyclotron is.
Well, I think the if I my recollection from Large Hadron Collider stuff is you've got like the big ring, but like to get to that big ring, they need to go through a few smaller rings to like get them. Like you got the little collider, and then they
Yep.
shoot out into a medium collider, and then it goes to the Large
The
Hadron
big
Collider,
boy. The big
the
boy.
big boy. Yep. Yeah. Particle accelerators. Fun for experiments. So that was paper one. There was
Have you
not too much there, but that's kind of the gist.
have you ever
Paper two.
used any sort of
Yes.
particle accelerators? I'm digressing
I have not.
slightly.
No.
I would like to.
No. It
That
sounds
would be
fun.
fun.
Did I think about? Yeah, even like working at Large Hadron Collider stuff. Like it always sounded fun, but I never really progressed to do any of that. It
Hey, you're
sounds
still
nuts
young.
though. Like the tidbits that I hear about the amount of data they
Mm.
generate on a daily basis. Like just in it that in and of itself, like the data challenge is mad.
hmm
They make so much data. I can't even give you a number. It's just like lots and lots every day. They can't even analyze it all because there's so much data.
That's amazing.
Crazy.
Lots and lots.
Lots and lots.
I mean, if anything, that is the biggest number, isn't it? Really, lots and lots.
Very big.
I always remember being at
Uh,
school and you say, "Oh, biggest number's infinity." Infinity's not a number. Well, you know what is a number? Lots and lots.
be rational here, Callum. Come on. Properties of 94. So this is paper two. So this is
Yes.
Kennedy, Seaborg, Segre, and
Macmillan.
Wall.
Macmillan.
No Macmillan. No
He's
Macmillan.
referenced. He's referenced. He counts.
Yeah, all right. He's got a citation. I think he's in the same group, but I don't know. They just didn't want to put him in this paper. So this is what, 2 or 3 months after that first paper. Same shtick. Submitted in May 41, but not released until 46 again. So yeah, interesting paper here. So it's only a page and a half. It's
hmm
again nice compact little thing. Yeah, what did you think?
Again,
What did you
super
make of paper
interesting.
two?
I noticed the little bit here on the first page where it talks about how they place the sample of uranyl nitrate into the paraffin block behind the beryllium target of the 60-inch cyclotron, and I just wondered why paraffin, which is a small
I
question
never thought about
in
that.
a big thing. Like, what is it about a paraffin block that's can they use something else?
That's a good question.
I love how
Yeah,
I
so
scroll here and it just Macmillan is highlighted, by the way, because I was searching for your name.
good. Um, yeah, so the experimental setup is like take a thing, put in a thing, put this with another thing, put this in some more stuff, and then put it in my big thing, and then watch what happens.
And then bombard it.
Um,
And I think
and bombard it.
is it
But why paraffin? That's a good question. I don't
This
know.
is
My
yeah, this
assumption would
is
be
bombardment with neutrons plus
yes.
deuterons. So both is being
Okay.
bombarded here.
All right. All right. Um, and I'm assuming they were just having different effects on what they impact. Like one knocks off some aspects. So yeah, I don't know what they're
Don't know.
doing.
Don't know.
Paraffin block. I'm assuming the uryl nitrate. Is it a solution? Is it a liquid?
I'm gonna assume it's a solid purely because it's got the dot 6H2O. So I'm assuming that's like crystallized.
Dot six.
Like
What?
in the formula for the uranyl nitrate.
All right. Is that what that means?
UO2NO32. Well, I only because I recognize that sort of nomenclature from looking at like hydrated copper sulfate versus anhydrous copper sulfate in school. Like that's
Okay.
how it's written.
Okay. And that's normally solid.
I'm just gonna Google it, mate.
Oh, yeah. Okay. So I guess if you take a paraffin block, I guess they just want to have like a lump that's going to sit there and be inert and do nothing
Yeah.
and not interact with their experiment. But that was my understanding of why they put it in
Yeah,
there.
it's a solid.
Hmm. Yeah. Okay.
It says
I
the
don't
wiki
prepare
the
that.
wiki entry says uranyl nitrate is a water-soluble yellow uranium salt with the formula UO2NO32 and then NH2O, where I guess N is the number of waters
Hmm.
attached to that salt.
Hmm. Okay. Interesting. But yes, so they took your paraffin block. They put that next to a beryllium block, and I think the beryllium block was that the deuteron bombardment? Beryllium from beryllium plus deuterons. Okay, so so they had a beryllium block next to our paraffin block, and this beryllium is our neutron emitter.
Yeah,
So it's like what you have in your school, where you have your
yeah.
alpha, beta, and gamma release or things.
Emitters probably the right word,
Emitters.
I imagine.
And you can have a beryllium block as well, and that can just slowly drop out
So
active neutrons.
I think I know the answer to this question. Why? So when you're thinking about a nuclear reaction, something like controlled fission, why is adding neutrons important?
I don't know,
I have
but
I have vague knowledge.
all I know there would be that that was a bit of a revelation around in this decade where they were bombarding atoms with or bombarding things with like alpha and beta particles, and like some of the Rutherford's work was taking lithium, bombarding that with alpha, and that
Hmm.
was novel. But shortly before, so this was what 1941. I think it was in the who started doing neutron stuff. I think it was in 1932. Charles Chadwick, someone Chadwick discovered the neutron, and it was
James
in
Chadwick, wasn't it?
1934 that Enrico Fermi was started bombarding uranium with neutrons. So like that, the concept of well, if I throw neutrons at that thing, it will do a different thing
Mm.
was
And I suppose,
still fairly fresh at that point.
yeah, maybe I'm asking my question through like future eyes in a way because
Yeah,
the question of why neutrons is probably not something these guys would have necessarily asked. It would have been, let's try neutrons instead of
maybe
why,
yeah.
you know? I imagine.
Do you have an idea of why? What's different between a charged particle like alpha or beta bombarding a sample compared to a neutral atom
I
like
don't know.
a neutron?
The only thing I can think, and I seem to have vague school recollections of this as well, is like you have an unstable atom which is very
Mm.
very heavy. It has lots of neutrons in nature. You know, if you think about like uranium 235, it's like two-thirds neutrons or just under two-thirds neutrons, and it's just adding those extra neutrons is what sort of tips it over the edge in a way and sort
Mhm.
of starts
Mhm.
that reaction. But again, that's like some ancient thought in the bottom of my brain. I don't know.
Yeah. Okay. I think there's also some discrepancy between I'm shooting really really fast neutrons at you and I'm shooting really, really slow neutrons at you. So
Yeah.
the if we look here at the experimental setup, they have the cyclotron, which is shooting really, really fast, 16 mega electron volt deuterons at your sample. So really fast particle accelerator. But the beryllium is just I'm a beryllium block slowly
I'm
emitting
emitting.
slow
Yeah.
neutrons to your
Yep.
to your sample. And I don't know, but I would anticipate that would be something to enable or foster the reaction they're looking for. So a fast bombardment of neutrons will probably just go, whereas your slow bombardment is probably just like,
A bit more
I'm gonna knock
controlled.
this particle off.
It makes me think of like inside reactors where they have the control rods, which are effectively
Ooh, yeah.
neutron. They're just neutron emitters, right? The control rods. So you take them out and it stops emitting.
Are they neutron
neutrons.
emitters or neutron absorbers?
Maybe you're correct. Control
I think they might be absorbers.
rods.
But yes, yeah, they're just doing
Yeah,
neutrony
you're
things.
right. Absorb neutrons. So yeah. What was I going to say? But I suppose it's still the same sort of idea, right? So the control rods are neutron absorbers, sorry, not emitters. And when they're in, they're controlling the quantities of the neutrons, is what I was trying to say, effectively. Which is true if they're emitters or absorbers, I guess. They will either way be controlling it. But they're definitely absorbers. I don't want to confuse people.
Yeah. All right. So what are we doing? We've got our uranium. We've stuck it in a bunch of kit, and we've bombarded it with some slow stuff, some fast stuff. And what did they do from there? So they bombarded this uranium. They made something else, and then from there, the rest of the paper is discussing how can we verify what we think is this new element, plutonium, is something else, and it's not uranium.
Yeah.
Because you can't look at it and say, oh, it's got a little uranium or plutonium sticker on it. That's what it is.
It's just got a different symbol. That's how you know,
It's just
Jamie,
got a different
obviously.
symbol. That's
it's
how
different
you know.
on the
It's
periodic
in a jar
table.
with a different label. Yeah, obviously.
It's on the periodic table. Just go and have a look, mate.
So some of the ways they were verifying this was if I have a look at what was it? Is the ratio of? Okay, yeah. So if I take my uranium, and I can measure the cross section of its interaction, and so this is a measure of how likely a particle is to interact radioactively. Was my understanding of cross section, and it's in the meters squared unit. It means the same as like cross section of an area, of a circle. And so they were able to verify they could do the ratio of a cross section from slow to fast neutrons from uranium, and that will give you some ratio. But if they took their new mystery particle and did the same test of what's the ratio of cross section, like what's the ratio of reactivity maybe from these slow neutrons and fast neutron bombardment, they could identify that it was different. So it was different to uranium, and so they was able to use that as an indicator to that this was a new element that was not just a uranium impurity.
Interesting.
But other than that, yeah, they kind of did it. They said, okay, we've got this particle. I verified it's now something else. Yep. I can measure it. Yeah. That was kind of it. There wasn't really too much more in there other than we did this thing. We saw this thing.
What was the name of the Russian bloke who got poisoned?
Mendeleev?
No.
I don't know.
Mendeleev, bro. In the news, Russian spy, radiation poisoning. Litvinenko.
That guy, yeah, that one.
He was plutonium. Oh no, he was polonium. Sorry, polonium-210 induced acute radiation syndrome. For some reason, I thought it was plutonium. What are you looking at?
Where's polonium on the periodic table? Polonium. What's the chemical symbol for polonium?
PO. Atomic number
P-O.
84.
84. Oh,
And
okay.
discoverer Marie and
All right.
Pierre
Yep. Okay.
Curie. We should do
Nice.
an ode to Marie Curie in this episode because I think she's one of my favorite scientists of all time because
All-time greats.
like in my head I call her the mother of modern physics. I don't know if that's like
Mm.
something other people say. I imagine it probably is.
Mhm. Mhm.
She I saw a YouTube video. I've watched lots of YouTube videos about radiation, as you can tell, and it was a guy who basically went to Marie Curie's lab and house, um, sort of the lab where she discovered radiation, and
Mhm.
he held a Geiger counter like to the doorknob, and it emits. And like the back of her chair where she would come out of the lab having handled these radioactive substances with no gloves on all day, put her hand on the back of her chair and pull her chair out. That top back of her chair is it contaminated when it starts to emit
Mhm.
itself?
I guess it's just radioactive, right?
Yeah, at that point it is
Mhm.
radioactive, right? Because I think there is two. There's irradiation and contamination. Uh,
Are there?
yeah,
That's cool.
irradiation is
Radio. Guess the radiation is it emitting actively its radiation.
so contamination occurs if an object has radioactive material introduced into it. But if the radiation is on the outside, it's irradiation, I guess.
Okay. Okay. Nice. Nice.
So yeah,
Um.
that's from BBC Bite Size. That is. Just googled it.
Good source. Yeah. Marie Curie, absolute boss of a scientist.
Yeah, and ultimately gave her
Unfortunate,
life
but
for it, right? Ultimately gave
yeah,
her life for the cause.
the things we learnt. Yeah, definitely. Definitely interesting.
I don't know what I was going to
Um.
say next.
Yeah. Where were you going with that?
I was gonna. So I mentioned Litvinenko because
Oh, yeah.
I
Polonium.
find
Yeah,
yeah.
we got there.
So I just find just like looking at the list of like symptoms and stuff because obviously when I teach about radiation, we
Mm.
look at the effects of radiation poisoning and things, and I was just hoping that I was going to have a wiki page there. But like, have you ever seen the pictures of him? I encourage you to Google it
I've
now
not. No.
because
Let's go for it. I'm
it's
not going to
a
Google him. I'm going to duck him.
it's very scary.
Oh. Oh, he doesn't look too hot.
No, and it was like a matter of days, right, from when it started
Mm.
to where it ended up, and I guess that just takes me cyclically back to the start and just saying I'm a little bit scared of radiation, you know.
Yeah, it really is terrifying.
For sure.
It's fine though. Like, we understand it now. We deploy it in a controlled environment for nuclear reactors. Great for power.
Hmm.
Bad for other things.
Yeah, definitely. So
Mm.
I guess we do some final thoughts.
Yeah. What were your takeaways from our double paper bonanza of?
So for me, I have really enjoyed again another little history lesson. I hadn't noticed what you mentioned about the fact that the paper was withheld until after the war, which I think is a really nice little tidbit to take away. Um,
Yep.
Again, I actually think you summed my final thoughts up quite nicely because like this was something that was novel and scary, and now it's something that we're able to use in a safer manner. And I just think
Hmm.
that shows a nice progression. Although I am going to pick you up on you said we know all about that now, do we? Who
Do
knows?
we?
Who
Maybe
knows?
not. Yeah, that's a good point.
I
All
imagine
right.
there's
Fair
always
enough.
new things to discover.
Yeah, that's good. Cool. I quite enjoyed the yeah, like I mentioned, how do you know it's a different element? But understanding what goes into the like scientific process for identifying is this a new thing? So yeah, that was quite nice.
I just love how we have such different takeaways. I definitely feel more emotive in that way, you know, in the sense that like I'm like thinking about how it makes me feel, you
Yeah,
know.
all right. I was thinking about, what's the
I love it.
technical demonstration here?
This is why we got on so well at school, I imagine.
Yep, yep. Anyway, that's us today.
That's us
Next
today.
time, I don't know what we're talking about. This time, we talked about plutonium. I hope you enjoyed yourself. Where can people find us, Callum?
You can find us wherever you get your normal podcasts,
Cha,
Spotify,
cha.
etc., etc., etc. You can also find us on YouTube at Osmosiscast. The episodes will be live in the video format, which is
Mhm.
we hope to see you there as well.
Awesome. We'll
Nice
see you
one.
around.
Thank
Thanks
you
a
so
lot.
much for your time. Bye.